Okay, let's check out the theorem 5.5, independence of eigenvectors. So let A be an n by n matrix. If v1 through vn are eigenvectors of A, corresponding to distinct eigenvalues, meaning like they're not duplicated, not repeated roots and that kind of thing. So lambda 1 through lambda n. Then the set is linearly independent and A is diagonalizable. So I decided to go ahead and go through this entire proof because it's a good one to try to get and understand. So we assume the hypothesis above, let A be an n by n matrix with lambda i's corresponding to v sub i's, just like it's stated. Okay, so this is a proof by contradiction, and I want you to try to study this like more than usual because you'll see these types of proofs later and later as you go through your math. Okay, so what we're going to do is first suppose that it's like you suppose the opposite. So suppose that the set v1 to vn is linear, oops, don't need that right there, is linearly dependent. So linearly dependent means, right, you can, well, they're not distinct. You can write one of the vectors as a combination of the other vectors. That's kind of the main idea. Okay, so then at least one v sub I is a linear combination of the other vectors, of the others. I'll just say other vectors. So what we're going to do is suppose that exists. So let's let v sub k be the first such vector. So be the first such vector. So what we have then is v sub k is equal to a linear combination of the vectors up to k minus 1. So d1, we're going to use d for our constants. d1, v1, etc., all the way to d sub k minus 1 to v sub k minus 1. And this set then, v1 to v sub k minus 1, so that set of vectors is linearly independent. So it's like you're going up, you're saying all these are independent, but the kth one is dependent. All right, so keep in mind that equation. Now what we're going to do is multiply both sides of that equation by lambda sub k, actually, the one corresponding to v sub k. Okay, so now multiply by lambda sub k on both sides. So what you get is lambda sub k, v sub k, equal to d1 lambda sub k v1 plus etc. all the way to d sub k minus 1 lambda sub k v sub k minus 1. So now similarly multiply by the matrix A on both sides of this one, not this one. You multiply by A on both sides. Okay, so then what you get is AV sub K equal to D1A V1 plus etc. to D sub K minus 1 AV sub K minus 1. And since AV sub I equals lambda sub I V sub I, this gives us, so this yields or gives us, so since that's true, this yields this equation. So we know what the A's are. So you get, so basically what we're doing now is we're going to substitute all of these for all of those. And then we're going to set these equations equal to each other after we've done that substitution. Okay, so you get lambda sub k, v sub k equal to d1 lambda 1 v1 all the way to d sub k minus 1 lambda sub k minus 1 v sub k minus 1. So then what we're going to do is we're going to look at these two equations. We're going to look at this equation. Let me increase it a little bit. We're going to look at this equation and this equation and set them equal. Not set them equal. We're going to subtract those two equations. So look at the left-hand side of those two equations. So we're subtracting the whole thing. I should probably make that clear. We're subtracting the combination of those. Let's just do it like that. Okay, so when you subtract them, note that these are the same. So the left-hand side is going to be 0. Okay, so let me state what we're going to do. Okay, so I just did little stars, basically. Star and star, star. Okay, so subtract. We're going to do star minus star, star. And we're going to subtract these equations. And we have, I'm going to move this up a little bit for now, 0 equal to, so little manipulation here, but it's just easier to write. You can look it up. D1 lambda k minus lambda 1 V1 plus all the way down to D sub k minus 1 lambda k minus 1 v sub k minus 1 where not all d sub i's equals 0 and lambda sub i's are distinct. Because that was our assumptions. So what that implies then is you have this equation equaling 0. So it's a dependence relation for v sub I. So what we get then, so thus a dependence relation for v sub i's where I is 1 to k minus 1. So think about that. We have the assumption that the d's are all non-zero. Okay, so let's go back to here. Back to here, we're making the assumption that this is linearly dependent. And so v is equal to this, and so this set is linearly independent, which means not all the d sub i's are 0, and the lambda sub i's are distinct. Okay, so then we get this by this manipulation, and we subtract them, we get 0 is equal to this. Okay, so if that's the case, then we have a dependence relation, right? Because otherwise all the d's would be 0. That if it's not a dependence relation. So because we're assuming it's not, you have that assumed. Thus, a dependence relation for the v sub i's from I 1 to k minus 1. We assumed that that set was linearly independent. So that's a contradiction right there. That is our contradiction. And in math, you don't see it in the books as much. Sometimes you put this little symbol down, which means contradiction. I'll write it out a little bit. So this is a contradiction. It's contradiction of the assumption that v sub 1 through v sub k minus 1 is a set of linearly independent vectors. So if that's a contradiction, you may conclude, therefore, the set v1 to v sub n is linearly independent. And if that's the case, by corollary 1, A is diagonalizable by corollary 1. Okay, so corollary 1 was the n space is the basis of eigenvectors, etc. Okay, so that's our proof. That took a little while, but it's a good one to study. I'm not like saying it's going to be on an exam because it's going to be open book, open note, but it's just in general a good technique to know how to do those. Okay, moving on, maybe some examples next.